This is a demonstration of the main topic of my project. The wheel is allowed to spin, but when the magnet is drawn close, the induced eddy current slows it down. This phenomenon is known as magnetic braking. This is the wheel spinning without the magnet, and its weight dropping. But when a magnetic field is applied, the speed changes drastically. In a magnetic field, a positively charged particle experiences a force in the direction of the cross product between the velocity vector and the magnetic field vector. Because in our applications the magnetic field and the velocity vectors are perpendicular, this force is perpendicular to the velocity. Because the velocity vector and the force vector are perpendicular, no work is ever exerted by the magnetic field. In our case, the spinning disk carries many electrons, which whirl around as previously presented when they encounter the magnet's magnetic field. These whirls of electrons are called eddy currents. These induced currents create magnetic fields of their own, which then in turn attract the magnet and essentially create a drag force on the metal. This is the code of the Arduino Atmel Atmega 328 microprocessor. It is written in a simplified version of C. The program begins by initializing a few variables and arrays, and prepares for serial communications at 10,000 baud. The next part of the program senses whenever the sensor reading goes over a threshold. This is done using a polling method. When the sensor reading exceeds the threshold, the time is recorded. This creates an array containing all of the times at which the sensor was blocked. After the program has collected 30 data points, it goes on to the communication stage of the program. In this stage, the program sends the time and distance array using capital and lowercase t as the start and stop codons. Between each element in the array, it waits for a handshake to ensure the information has been sent. This is the data acquisition and graphing code for the computer end of my experiment. It begins by reading 13 characters from the serial port using the Linux cat command. It then parses the characters using the capital T and lowercase t codons. Once the characters have been parsed, it converts them to integers. Then the acquired data undergoes a series of feedbacks and logic gates in order to ensure there have been no errors in communications. If the data passes the tests, it's stored in an array. The program then sends a handshake character, ensuring that the data has been received. The process is repeated until all of the data has been acquired. At times, this can take up to 6,000 iterations. The data is then sent through approximation VIs, and 2 derivatives are taken. Each of these processes creates new individual arrays, which are then sent to the built-in graphing VIs provided by LabVIEW. Here we will see how all the processes come together. The microcontroller records each time the tabs on the wheel block the sensor. It creates an array and sends it through the serial communications on the computer. Here in slow motion you can see the data being sent. This is the data recorded for free fall. The x-graph is a typical parabola. The velocity graph is a straight line with a positive slope, and the acceleration graph is a straight line after the weight is released. These are the typical results of a weight drop with magnetic braking. It is analogous to drag and terminal velocity. The velocity graph resembles a 1 minus e to the negative x, and the acceleration an e to the negative x. The next two slides will show similar results when the magnet is moved closer.